So, scientific approach to knowledge. Scientists approach learning about things in an organized manner. Our approach is empirical. That means it's based on observation and experiment. This makes it different from philosophy. We don't sit around and think about things and discuss ideas. We're making observations and testing our observations with experiments. So the scientific method is the name we have for this process that scientists use to understand nature. The key components of this are observation, formulation of hypotheses, experimentation, and then formulation of laws and theories. And we'll talk about each of these individually. So observations, also known as data. You measure something. You go to the doctor and they always measure how tall you are and how much you weigh. Those are observations. Those are data. Data observations can also include descriptions of something happening or colors or things like that. Descriptions about the characteristics or behavior. We'll be mentioning some scientists and some historical things throughout the semester. I think those are an important part of learning chemistry, but I am not going to test you on history, okay? So I will not give you any questions about what did Antoine Lavoisier discover, where did he live, what time period did he live in. I'm not going to quiz you on any of that, okay? But he did live in the 1700s. That was a long time ago. He was a French scientist, and he studied burning things. He liked to burn things. How many of you like to play with fire? Yeah, I think a lot of people who like science like to play with fire. It's fascinating, right? Secret pyromaniacs, that's what chemists are. So think about burning a log in the fireplace. That's a safe way to play with fire. You put this big old log, it's heavy, into the fireplace. You have a nice fire if you can get a burn day. And then what does the log look like after the fire's out? Ash. It's ash. It's mostly gone, not completely gone, but most of it's gone. Does it weigh the same? No, it's much lighter, and it's not one solid piece anymore. It's all these flaky pieces that'll just float all over the place and make a big old mess. Something happened to it, right? Well, what Lavoisier did is he combusted things in closed containers. So he had a sealed container, and he would weigh it, and then he would burn the thing inside that sealed container. Then he'd weigh the container again. And he made the observation that when he did this, the mass didn't change. Okay, so that's different than the observation you make about the wood in the fireplace, which is not a closed container. So we make an observation, and that often leads us to formulate a hypothesis. The hypothesis is a tentative interpretation or explanation of why that happened. At this point, we're not claiming that this is correct. We're saying this is my best idea. I think this is why it happened. So Lavoisier looked at these observations and he said, I think that when that substance burns, it's combining with something that's in the air. So he had this container. There was air in there, and there was the object he was burning. After it's burned, the whole business weighed the same amount. He says, well, I think it's combining with something in the air. In order for a hypothesis to be useful, it needs to be something that we can test and possibly prove false. It needs to be falsifiable. So you can come up with a hypothesis sometimes, but there's no way to test it. Well, that's not useful. You have to come up with something that we could actually test and see if it's correct. How do we test a hypothesis? We do experiments. Experiments, in order to be useful, need to be controlled. We can't just say, oh, well, let's try this, let's try that. Sometimes we do that, like in real life. Oh, well, I don't know if these cookies, they didn't come out right, so next time I'm going to add some more sugar. But maybe I'm going to change something else too. A scientist will change one thing at a time and very carefully make observations so that we can learn the most. So the results of this experiment may prove the hypothesis or may support it. You can't really prove it. Support it or may prove it to be wrong. No, that's not correct. One of the things you could test with his hypothesis that something that burns is combining with a component of the air, you could try putting it in a chamber that has no air in it. and try to burn it and see what happens. Now that we understand how combustion works, if you do this in a chamber without any air, it's not going to burn. We now know that it requires oxygen. Oxygen is the component of air that causes something to be able to burn. So we do the experiment. What if our hypothesis is wrong? There's two options. You can modify it. Maybe you just need to tweak it a little bit. Or sometimes you have to chuck it out the window. It's like, man, I was way off base, and this experiment shows that. Okay, so the next step in the scientific method after the experimentation is laws and theories. Laws and theories are often confused by students, and they have a very distinct difference. A scientific law is a brief statement that summarizes what has been observed in the past and can be used to predict future events. One law that you might be familiar with is the law of gravity. Okay, so here I've got a Sharpie, well, it's actually an off-brand Sharpie, a marker, and I'm holding it out at shoulder height. What is going to happen according to the law of gravity if I let go of this? It's going to fall to the floor. It does that every single semester. It did that yesterday too. Law of gravity. It says what will happen, and we can use that to predict behavior. Many of these scientific laws, like the law of gravity, that is something you probably learned intuitively as a young child. It's really interesting to watch babies learn about the world. I've had a lot of experience watching babies learn about the world. They throw stuff and they do all these crazy things. They are miniature scientists investigating the universe. Okay? And so they throw things, and they find out that when you throw something up in the air, it comes down, and that maybe you don't want to throw something hard and pointy straight up because it's going to come down and land on you, and that hurts. Right? But the law doesn't explain why these things happen. Another law that we need to talk about is one that Lavoisier came up with after his experiments on burning things. The law of conservation of mass. This says that in a chemical reaction, matter is neither created nor destroyed. So he burned things in a closed container, and the mass of the container and its contents didn't change. Now, obviously, something happened to the stuff inside, but there was no mass created or destroyed. It just got changed up. Scientific laws can also be experimented upon and tested. And sometimes new developments come up, and we realize, okay, that scientific law is not quite valid anymore. You cannot choose to violate a scientific law. It just says what happens. Occasionally you'll hear about people who apparently tried to defy the law of gravity, and they'll jump off a building. It doesn't matter what you believe. If you jump off of a building, you're going to fall down, and you're probably going to get hurt. So you can't just choose to disobey it like you could disobey the speed limit. It's very easy. You can speed on the highway, and you may have some consequences, but you can break the law. You can't break a scientific law. So scientific laws describe how nature behaves, but they don't say why. That's what theories do. A theory can be come about from one or more well-established hypotheses. So this is more of a group effort. Someone has a hypothesis, they test it, other people hear about it. That's why we publish journal articles to say, look what I found. Other people say, well, I'm not so sure I believe you, and so they test it also. And after this has been tested for a while, that hypothesis may become a theory, explaining why this stuff happens, right? So a scientific theory is a model for the way nature is and tries to explain why it does that. So back to our example of burning things, the theory that came out of that eventually belongs to John Dalton. He lived a little bit after Lavoisier. He came up with his atomic theory to explain the law of conservation of mass. And his proposal was that matter is composed of small, indestructible particles called atoms, and that those particles are merely rearranged in a chemical equation instead of being destroyed, and that's why the total mass remains the same. So if we go back to the Legos, imagine that you made a little tree out of Lego bricks, okay? So it has a given mass. If you take those bricks and you take them apart and you rearrange them and you make two bushes, two little green bushes out of Legos, did the number of Lego pieces change? The number of bricks is the same. Whether you choose to use all of them in your new thing or not, Lego bricks do not just appear and disappear. I know that sometimes they seem to do that. When that one piece you need is like seemingly vanished, it doesn't actually disappear. It's just hiding under a couch cushion. And sometimes it seems like they appear when you're walking through the living room in the middle of the night and you step on one barefoot and you go through the ceiling. But they really do not appear and disappear, and neither do atoms. In a chemical reaction, what's happening is the atoms are coming apart and being put back together into different molecules. And so the amount of stuff remains the same, even though it may appear very different. So now we know that when the wood in your fireplace burns, two of the major components of the products of that reaction are the formation of carbon dioxide and water. And those both form in the gas state, and so the carbon dioxide is most likely just going to go up the chimney with the hot air. And that's why the log weighs so much less afterwards, because a lot of the atoms that were part of it have gone into the air now. When you do that in a closed container, those atoms can't escape and the overall mass remains the same. Any questions? Theories can also be tested, validated by experiment. A concept that's a little hard to get your mind around is we can't prove things to be correct, because someone may learn things about what we're studying in the future, like, I should have a good example of this. I can't think of one. Think about before we had microscopes, before we could see bacteria and blood cells and things. People didn't know what was in blood. They didn't know what it was that was making people sick. And so they could have tests and experiments and theories even of what was going on, but because no one had invented the microscope yet and we couldn't see those smaller particles, they could not fully understand what was going on. And so theories are going to be limited by the current state of technology, really. So when we have a theory, you could prove it wrong by experiment, but you can't prove it correct. We can only say, well, to date, we have nothing that disagrees with this theory, and so we're going to accept it as true for the time being. Theories are as close to truth as we can get in science. And so in everyday life, we'll say, oh, well, that's just a theory. Meaning, oh, you just got some crazy idea about how stuff works. In science, it's not just a theory. A theory is a very significant thing. So here's a kind of a flow chart, sort of summarizing the scientific method. And the scientific method is not a set of do this, do this, do this, and you will get this at the end. It's just more of an approach. It can be very, very messy when you actually are doing it. So you may start with an observation, and you develop a hypothesis for that, and then you have to test it with experiments. The results of the experiments may confirm your hypothesis, or they may disprove your hypothesis, in which case you need to revise it or start over. Sometimes you end up going in these circles for years. Observations can also lead to laws. Law of gravity. We observe that when you drop something, it falls. Well, then that gets tested. So, well, maybe this thing won't fall. And so you test it. That's what little children are doing. They're testing gravity. That's why they throw their food off the high chair tray. They're just testing the law of gravity. So you test it, and it may be confirmed or disproved, and you have to revise it. And so you can go around in this circle a lot, too. Laws can lead to a hypothesis. Hypotheses can lead to theories. Theories also are tested by experiments. Okay? So it's just an overall process that we do. So this is the sort of question which could show up like on an exam. Which statement best explains the difference between a law and a theory? So A, a law is truth, whereas a theory is a mere speculation. A law summarizes a series of related observations. A theory gives the underlying reasons for them, or a theory describes what nature does. A law describes why nature does it. Any ideas? The answer is B. Okay. C, it sounds kind of good, but it's exactly backwards. The theory says why. The law says what. So that one's backwards. And theories are not mere speculation. Any questions?